Alright, so in this video we're going to do some examples of things that are and are not ideals and factorings, just to get a better feel of what these are, just having some abstract definition. So just as a quick, an ideal is a subring of some ring that has the property that when you multiply some element in your big ring times something in your subring, the resulting product is still going to be in your subring, and that makes it an ideal. So in the last video I kept referencing the example of the real numbers and the subring of integers. And so you might ask, well, are the integers an ideal? And I think I kind of did this in the last video already, but if you take, say, pi as a real number, that's not a very good pi. Pi as a real number, and say, I don't know, 3 as an integer. If we multiply these together, we get 3 pi, and that's obviously not an integer. So we just took something in our ring R and something in our subring Z, multiplied them together, and we got something that was not in our subring. So that this one counterexample completely disproves the integers from being a ideal of R. So then you might ask, okay, well, if the integers didn't work, well, maybe let's go up one level, so to speak, and maybe the rationals will be an ideal. Well, really just do the same thing. I mean, 3 is a rational number. Pi is something in our overall ring. We multiplied these together, we got 3 pi, and that's not a rational number. So the rationals are also not an ideal of the real numbers. Okay, well, maybe if we take the rational numbers and as a subring take the integers, maybe that'll be an ideal. Or maybe the integers will be an ideal in the rationals. Well, let's take a rational number, say 3 halves. Multiply that times an integer, say, I don't know, 5. And that gives us 15 over 2, which is not an integer, again. So the integers are not even an ideal of the rational numbers, not an ideal of rationals or the reals. Alright, so those are some examples of things that are not ideals, and I mean, obviously I could do more, but I think you're probably getting bored at this point. So let's look at some things that are ideals. So maybe we'll look at the integers as our big ring, and as our subring, as our candidate for being an ideal, let's look at 2 times the integers, or in other words, the even integers. Which I guess I'll write this out. This is the set of all 2 times x, where x ranges over the integers. And sometimes you'll also see this written as the ideal generated by 2. And I think in one of the very first videos I did, I proved that something looking like this was a subring of the integers. I think it was 3z. And so I'm not going to go ahead, I'm not going to prove that this is a subring. If you want to do that, go ahead. But I will prove the ideal part, though, the absorbing part. Well, I'll more talk you through it. So this is the set of even integers. Now, if we multiply any integer in z times one of these even integers, as we know, either an even or an odd integer multiplied by an even integer is always going to give you an even integer. So in other words, what that says is anything in z times anything in 2z is still an element of 2z. And that makes 2z an ideal. And so with that, we can even talk about, since it's an ideal, we can talk about a factoring. So we can look at the set of cosets of z mod 2z, which there's really only 2 of them. This is the set of 2z, which is our even integers. and 1 plus 2z, which is our odd integers. These are the only two cosets we have in this factor ring, and so maybe you're asking, or you're saying this looks like a very strange ring, and if you maybe you're thinking back to our ring definition and you're wondering, well, what is the zero of this ring? And the zero of any factor ring is always going to be whatever coset that you mod it out by. It's 0 plus your coset. So in this case, 0 plus 2z, which is just 2z. Usually you won't really see it written as 0 plus 2z. You'll just see it written as whatever ideal you have. And this is your 0 of this factor ring. So if we add this to any other element, there's only one other one in this case. If we add this to this other element, it's going to give us that element, because here, I'll write it out. So 0 plus 2z plus 1 plus 2z. This is the addition of cosets that I defined in the last video. The way we add these up is to add their representatives. So in other words, we're going to do 0 plus 1, which is just 1, and then plus our ideal. And that's the way that we add these together. And then, so as you can see, that adding this element here did nothing. It didn't change this this coset at all. It just gave us that coset. This is really our definition of what we defined as a 0 element. And so maybe what happens if we multiply these instead of add them? So 0 plus 2z times 1 plus 2z. Well, just like we did with the addition, we're just going to multiply the two representatives together. So we get 0 times 1, which is 0, plus 2z, which is our 0 element. What happens if we add 1 plus 2z with itself, plus 1 plus 2z? Well, again, we're just going to add the two representatives. We get 2 plus 2z. But now 2 is already an even number. We could also represent this as 0 plus 2z, or just 2z. Since 2 is already in there, just choose a different representative. Choose 0 to represent this coset instead. So 1 plus 2z plus 1 plus 2z is just 2z. And maybe this is seeming kind of familiar to you, and as a sneak peek of things to come, we would actually say that this is isomorphic to the ring 2z2. But that's kind of getting ahead of myself there. So that's basically just saying that this ring is structurally equivalent to the ring Z2. But don't worry about that. Alright, so moving on to a more general example of what we just talked about. If R is a commutative ring, and if A is some fixed element in R, then the set of A times R, which is defined as really just A times R, A times everything in R, this set is an ideal. And I will go ahead and prove that. So this is A times R, where it is A times every element in R, where R ranges over R. So I'm not going to prove the subring part because that's pretty straightforward. I'm going to prove the absorbing property part. So let's let X be some arbitrary element in our big ring R, and Y be an element in this ideal here, the thing that we're proving is an ideal. Okay, so if y is in there, then that means that y is of the form a times r for some fixed element r. For some r in r. Alright, so then if we multiply these together, this x and the y, x times y, well, we can make this substitution. We get x times ar, so x times ar, and then since this is commutative, we can write this as a times x r. And if we put parentheses around that, we see that xr, that's an r, xr is an element of our big ring R. So we have a times something in R, which is the exact requirement for being in this set here. So this is an element of AR. And since multiplication is commutative in this case, this is a commutative ring, this is also equal to yx. So that pretty much proves it here. I didn't prove the subring part, but this is the absorbing property of ideals. So this is an ideal of this commutative ring R. In general, if you let z be the integers are a commutative ring. If you multiply any integer times the integers, like that's what we were doing up there, we had our a was 2 in that case. So you can pick any integer there, so say like 6z will be an ideal of z. Any number here will be an ideal of z. So in the case of the integers, if you have some arbitrary integer a times z, that'll be an ideal. And so since it's an ideal, we could talk about the factor ring. So z mod az. This is the set of cosets of this az, where the a is some integer. And this will be a ring, and it'll the number of cosets that you have in this particular case will be a. Like up here, we had 2, and since we modded out by 2z, we had 2 cosets. Similarly, if we have 6z, we're going to have 6 cosets. And so in general, if you have az, you're going to have a cosets. That is, of course, the a that you choose is minimal. So like, never mind, sorry. What I was thinking of was like you could choose a negative number here, like -6. But then it wouldn't make sense to have -6 cosets. It'd be the absolute value, but I think you get what I'm saying. So I think those are the only examples of ideals that I have at the moment. Once we start talking about polynomial rings, we'll have a few more examples to work with, but I think that's it for now. The next video I do, I think, is going to be on some properties of ideals. So stay tuned.